About number systems. The objectives for today are simply going to be understand that there are different number systems and be able to convert from one number system to another. Okay, so we're going to go ahead and start with something that we're really familiar with, and that is decimal numbers. Okay, and so decimal numbers have what we call base 10, meaning that there are 10 digits in the number system that go from 0 to 9. So we count from 0 all the way up to 9, and then when we run out of numbers in our number system, we simply then start to repeat numbers. So we'll get up to count all the way up to 9, and then we'll put a 1 in front of it and we'll count again. So we'll go 0 to 9, that would be 10 to 19, and then we will increment the 1 to a 20, and so on and so forth. So you're very familiar with that. That shouldn't be any new information there. But let's go ahead and start with a decimal number here, 4096, and I'm going to go ahead and put a tiny little subscript 10, signifying that this is base 10, and we're going to kind of break this down. So we know that this is the number 4096, but how do we really know that? Like what is the proof that that is the number 4096? And to do that, what we're going to do is we're going to break this down into its place values. And so we know that this is going to be the ones place, right? And we know that this is the tens place. And we know that this is the hundreds place. Okay, and we know that this is the thousands place, right? And what that really means is these are all powers of 10, right? So the ones place is actually 10 to the 0 power, and this would be 10 to the first, and this would be 10 to the second, and 10 to the third, and then we can just continue that all the way down, however many digits we have there. And so then if we were to, say, multiply each number by its place value, so here we would have 6 times 1, which would be the ones place, so 6 times 1 would give us 6, and 9 times the tens place would be 90, and then 0 times the hundreds place would be 0, and 4 times the thousand, which would be 4,000. And we can add all these things up, and what we're left with is the number 4096. Okay, so it proves that that this is indeed the number 4096. But what I want you to take away from this is the fact that there are place values. Those place values are all powers of 10. And that's going to become important as we kind of move forward here. And so the next number system we're going to look at is what we call binary. Okay, and binary is very similar concept here, but instead of having 10 numbers in the base, we're going to have 2 numbers in the base. Okay, and so those 2 numbers are going to be 0 and 1. So that's the highest that we can go to. So if we were going to say count in binary, we would start with 0, and then we would go to 1, and then we are out of numbers. So we need to set another place value. And so now it would be 10, and then, or 1, 0, and then we would continue to count like so. So we would end up with, this would represent our 0, this would represent 1, this would represent 2, this would represent 3, and we could just continue with that. Every time we run out of numbers in the base, we add another number and continue like that. So that would be 1, 0, 1, 1, 1, 0, 1, 1, 1, and we can continue counting, having these representations of decimal numbers in binary. So we've counted all the way from 0 to 7 in binary. Okay, so computers, so why is this really important? You know, computers and digital logic use binary because we can simplify the 1 and zeros as, you know, whether something is on or off. It could just be a digital or a logic high or a logic low. So we can represent decimal numbers, we can represent other data in computers. But in order to really for this to really be able to be useful, we need to be able to make the switch, right? I need to be able to go from binary to decimal and decimal to binary. And so we're going to take a look at that, and that's really the goal for today, is to learn how to interchange. Like, for example, how can I prove that that is 0? How can I prove that that is 4? And so we're going to have a method to do that. And so the first method that we're going to look at is very similar to what we did right here with the number 4096, and that's what we call weighted multiplication. Okay, and in this weighted multiplication, we're going to take this number. Okay, so let's use a binary number here. I'm going to say 1 0. Let's make it a big one. So 1 0 1 1 0. Okay, I don't know what that number represents right now, but with this method here of weighted multiplication, we can figure out what that number is in decimal. Okay, so what I'm going to do is very similar to what we did over here. We're going to look at the powers, right? But over here we did the powers of 10, right? We did because that was base 10. So decimal is what we would refer to as base 10, right? Binary, on the other hand, only has 2 digits, so we're going to call this base 2. So we're going to have each of the powers here. This is going to be 2 to the 0 power. It's going to be 2 to the first, 2 to the second, 2 to the third, and then 2 to the fourth. And what that represents then is our place values. And so here we would have the ones place. Then we would have the twos place, and then the fours place, and then the eighths place, and the 16ths place. And what we can do is we can multiply the number that is in each of the places by its place value, and just like we did here with 4096. So in this case, it would be 0 times 1, and that would give me a 0. And then 1 times 2, that would give me a 2. 1 times 4 is 4. 0 times 8 is 0. And 16 times 1 is 16. So in this case, if I were to add all these numbers up, what we would end up with is 16, 20, 22. And so the number 10110 base 2 is actually the number 22. It represents the number 22 in decimal. So that's how we would go from a binary number over to a decimal number using this strategy called weighted multiplication. Okay, it's pretty simple to do, and actually you can do this with any base that you want. It always works out. So for example, there's another number system that's utilized often in computing, and that's hexadecimal, and that's where you have base 16. And this same strategy works with hexadecimal, this weighted multiplication. So looking at the powers of the numbers using the base. So in this case with binary, it would be base 2. In hexadecimal, it would be base 16, so it would be 16 to the 0, 16 to the 1, so on and so forth. And simply multiply the number by its place value, and you would get, and add it up, and you would get your decimal number. So then we need to be able to go the other way. And so I'm going to kind of erase here because I'm running out of room. But let's erase all this. Okay. And so then the next way, the next strategy that we're going to do is we're going to go from decimal to binary. So we already know that this here, we have this number 22. So we know that 22 is 10110. So let's use 22 again, just so that we can prove it works. But we're going to do something now to go from decimal to binary. We're going to go use what's called successive division. Okay, and in successive division, in fact, I actually like to call this the birthday cake method. So the birthday cake method. And it makes it pretty easy to do. So I'm going to start down here because I want the bottom of my birthday cake to be way down here. But we're going to start with the number 22. All right, and what I want to do is I want to divide it by the base in which we're trying to convert to. So in this case, I have the number 22, which is base 10, and I want to convert it to base 2, which is binary. So 2 goes into 22 11 times. And there is no remainder, right? So remainder is 0. And then we're going to start building the birthday cake. So we're going to say 11 divided by 2. Well, I know that that goes into 11 5 times, and the remainder happens to be 1. And then we're going to divide this by 2. And 2 goes into 5 2 times with a remainder of 1. And then we have 2 goes into 2 1 time with a remainder of 0. And then we're going to take this one. We're going to continue to build the birthday cake until I get a 0 on top. So in this case, now I have 1 divided by 2. Well, 2 goes into 1 0 times, and we would have the 1 left over. So we're going to go until we get a 0 on top of the birthday cake, and we are going to now have our binary number. Okay, and so some important things you need to look at here. This top number is what we call the most significant bit, meaning that this is the highest place value, or it's going to be the number that's on the left-hand side. This number is what's known as the least significant bit, which is exactly the opposite of that. This is the ones place. So this, in this case, this would be our 16s place. This would be our ones place. And so to write this number, it would be 22 base 10 over to binary is 10110, and that's base 2. And usually you use these little subscripts just to ensure like there's no confusion. So like this could be 10110 base 2, or if we didn't have the subscript, somebody might read it as 10,110. So again, when we're going back and forth between number systems, it's important to have that little subscript so that you know which number system you're talking about. So in summary, we have 2 main methods here. If we want to go to from decimal over to binary, we're going to use the birthday cake method. If we want to go from binary over to decimal, we're going to use this weighted multiplication. So we have 2 methods for converting one to another, and as you get good at this, you'll find that there are even easier ways to do it. You kind of get the hang of it, but I'm going to leave that out. I'm going to stick with these 2 methods for right now. So let me know if you have any questions, and best of luck.